Hello everyone. Welcome to today's discussion, wherein we are trying to understand stability with respect to root locus, with respect to S plane. That is, root locus is about S plane, and then bode, that is frequency domain. What will take bode, and then time domain analysis. If a system is stable, how it will be reflected in these three domains. At the same time, if the system is unstable, how it will be reflected in these three domains. Okay. To start with, let us look at a built-in GUI which is available in MATLAB. The GUI name is margin GUI. You can see here that margin space GUI gives you error because the actual built-in library to access that built-in library is margin underscore GUI, all in small. Okay, again, see the space left will give you wrong error, so you should not leave any space. And then now it is opening a new window altogether. Now let us take this as an example and try to understand how a system responds, and when it responds, whether the system is stable or unstable. So first you can look at this kind of right side where I am pointing the mouse. Now this is a system given to us. Now in this kind of system, k is a variable where k could be any simple proportional controller value. K could have any value from 0 to infinity. So this k is connected in feed forward path. Along with that, our actual plant GFS is connected. Now here you can see what is my GFS. GFS is given by a transfer function 0.5s plus 1.3 divided by s cube plus 1.2 s square plus 1.6 s. Okay, this is a plant transfer function. And when a feedback is taken, which is a unity feedback and given, this becomes a closed loop transfer function. Now this is a built-in program for a variable k. If I vary the k value, this controller k value, what happens to system output? Now I can look at the output in two aspects, from bode plot aspect as well as time domain aspect. Now I will not go into all. If I just take a k, if I move this, you can see that the outputs are changing. So this itself will give you some idea. Now if I take you, I have already tested this for a k value of say 2.7, roughly around 2.7. Okay, around roughly, you can see that gain margin is 0.13, just stable. Okay, it is in the verge of instability, and you can see phase margin also positive. When both are positive, the system is stable. But you can see even this one also shows it's stable. But when I make it 2.8, let us look at what happens. Okay, just 2.8. Okay, somewhere close to 2.8 is also okay. Okay, it becomes a negative 2.8 or 2.9. It becomes a negative. So when this becomes negative, gain margin and phase margin, the system stability is becoming unstable. So that you can check. Now let us try to understand these things by writing a program ourselves rather than depending on this GUI. And also we look at the root locus, which in most of our textbooks there is no comparison between root locus, bode plot, and step response, which is in a way is like comparing same system in time domain, in S domain, and in frequency domain. So I am trying to do that with this example. So I am trying to take this transfer function. Remember, the transfer that I am going to take is 0.5s plus 1.3 plus s cube plus 1.2s square, 1.2s square plus 1.6s. Now coefficient of numerator is 1.5, sorry, 0.5 and 1.3, 1, 1.2 and 1.2, which is required for my programming. Okay. there's a piece of code which I have already written. Now, if you are interested to write it again, yeah, you can pause the video and write it again. So, as I said, the transfer function that we are taking is 0.5, numerator is 0.5 and 1.3. This is of g of s, that is a open loop transfer function. You can, what I am trying to say is, this is only about g of s. I am not putting it in a closed loop and checking. So, my g of s is 0.5 and 1.3, and denominator is 1, 1.2, 1.6, and there is no s to the power 0 term, so it is coefficient is 0. So if you by mistakenly, if you consider this, if you forget this, then it becomes s square plus 1.2s plus 1.6, which is not correct. So you have to put 0, which is s to the power 0. Okay. Once I consider numerator and denominators of open loop transfer function, which is g of s. Now my g of s is given by a built-in function called tf, which is a numerator comma denominator, or I can write here. Anyhow, you will get to understand this. Okay, as you use MATLAB. So once I have my, let us look at what is my root locus. Okay, so I am uncommenting root locus, and I am commenting any of things that is not required. So this will help me plot. Okay, let me run this. So only I am looking at these 4 lines of code. So my interest is in this, and remember, in this g of s, I am not multiplying any k, because k is made to vary from 0 to infinity. So let k be anything. The root locus itself is trying to increase k value automatically inside. If you see at the block, the k is varied from 0 to infinity. Now the root locus, idea is, when you close the system, when the system is open loop, when you close it, whether the system is stable or not. So hence, k, you should not play with k in root locus, and you should consider open loop transfer function. Using open loop transfer function, you are trying to find out whether system is stable or unstable. So let us run this. Okay. Now when I am trying to run, so you can also check before root locus. You can check the transfer function that we have taken, 0.15, 1.3, 1.3. So this is what we have taken. So is it correct? So we can just verify once, and then let us look at root locus. Now when I am trying to understand the plot of root locus, you can see that the roots are moving in right side, so of imaginary axis, which suggests that at certain value of k, system is becoming from stable system to unstable. So for initially k equal to 0, the roots originate from poles, open loop poles, and then end at open loop zeros or infinity. So in this case, they are moving towards infinity, and they are just crossing geometry. So at this point, system is become stable to unstable. So at this point, if I look at what is k, just click on it. So gain is 2.56. Now as we have seen that we are interested in 2.7, so let us try to move this a bit. Okay, 2.75. Okay, even this also will give you If you look at what is the pole position, x-axis is at positive and y-axis is also at positive, because y-axis is above this, and my interest is x-axis. Since x-axis is not right side of 0, that is in this case it is right side of 0 because it is positive. So I am interested in left side. Okay, anything close to 2.7. Okay, now let us look at 2.66. You can make it as close as to 2.7. You can see that negative sign, negative symbols, this tells you that x-axis is left side of geometry axis. Okay, so let us look at 2.7, and if I just cross this geometry axis, which is close to 2.8, yeah, I can stop it. Okay, you can also try 2.78 or 2.85. Okay, now it is positive. So this suggests that system was stable, and now it is unstable just because crossing. Now this is our understanding in root locus. So let me close this. Now I just want to understand the same thing with the time domain analysis. In time domain analysis, so for that I will just comment this. I don't want to see my root locus, but I just should know that at 2.7 system is stable and 2.8 system is unstable. Now I am plotting two values for k equal to 2.7 and 2.8 with increment of 0.1. I just need two graphs, so I don't want to confuse too many things. So let me plot step response. So I will just uncomment this step response. Okay, let me run this. Okay, now I can't see the graph properly because you can see that x-axis is running 14,000 times, and because of this I can't see much. Now there are many options. I have to limit this x-axis. So in the programming itself I can write xlim. I just want to see, say, 0 to 500. I have done trial and error. You can also try. If I say xlim, then if I run this now, no, yes, now I can see there are two graphs. So this is at 2.7, this is at 2.8. You can see that in 2.7 oscillations are damping, that is reducing. Okay, but at 2.8 oscillations are increasing, which is just reverse of what has happened earlier. So it suggests that at 2.7 system is going to reach its final value. Okay, so that is bounded output, whereas for 2.8 it is becoming unbounded because you don't know what is the value, it is keep on growing. We have also seen the same thing now without putting this xlim. If I want to understand, now you can see that the oscillations are growing, so it is much higher. You can see 10 to the power 27. So these values are called unstable systems. So at 2.7 system is stable, at 2.8 system is unstable. This is with respect to time domain. Now let us look at the same thing with respect to frequency domain. So here we have taken bode plot, and another thing that I have to highlight before I go to bode plot. Now look at the transfer function that we have considered. Now transfer function that we have considered is k into g of s divided by 1 plus k into g of s into 1. So this is just considering this. This is a, if I want to find step response, I should consider closed loop transfer function. Now closed loop transfer function of this is k into g of s divided by 1 plus k into g of s into h of s. h of s is 1, so I have considered this. So I have to write this in this way. So that will give me step response. If you by mistakenly consider g of s here, then you are getting a different output. So kindly use closed loop transfer function while finding step response. Okay. Now let us look at bode plot. So for bode plot, again I am considering 2.7 and 2.8, and I am giving a pause of 20 seconds because I need to understand what's happening in between that. Okay. So I am interested in finding out whether system is stable or unstable, and more importantly at k equal to 2.7 whether system is stable. So I just have to multiply k into g of s again for a given value of k. G of s is assuming that k equal to 1. But if I want to have at k equal to certain value, so I have to multiply that k. My open loop transfer function will be k times g of s. Okay. Now into 1, of course, because there is a feedback. If I want, I can write, but it doesn't add much to my mathematics, because if you cut this break open, if you stretch it, make it straight, k g of s into 1. So that is how we have to understand. So k into g of s into 1, that is the open loop transfer function. But k is considered to be 2.7 and 2.8. Let us run this with a 20-second pause, so I have to do it quickly. Okay, now this is my bode plot. So let me plot all the margins, all stability margins, and point out what is my gain margin. Gain margin is positive, and at the same time phase margin is also positive. So which suggests me that system is stable. But gain margin, if you look at, just it is 0.14 at this. So it is very small margin. That means the stability level is very less. So it is likely to be unstable if you have a variation of gain. That is the meaning of this. Now we just got another plot within this 20 second. Okay, let us look at the second one output. So I'll point to that second case. Pointing at the second graph, I am trying to understand. Minus indicate that system is unstable. Okay, this is what we understood, and same thing we can also check from this graph here. Minus 0.463, it's again unstable system. When both are minus, it is unstable. So this understanding will tell us that system is unstable for 2.8, system is stable for 2.7. This is the understanding with respect to root locus, with respect to time domain analysis, with respect to bode plot. Okay, let us try to plot everything in a one common output. So let us use subplot for that. So subplot 1 3 1. So that is my first subplot for root locus. Then let me use subplot for time domain as 132, and similarly for bode plot 133. Okay, so let us understand all the things at once. Okay, look at output. Okay, so what we did, yeah, we just forgot to uncomment this. Yes, sorry. Okay, pause. Let us run again. Okay, the root locus which says at k equal to 2.7 system is stable, at k equal to 2.8 system is unstable, and the step response at k equal to 2.7 says system is stable, and at k equal to 2.8 system is unstable, and the same thing holds good here also. The system says at 2.7 system is stable, and at 2.8 system is unstable. So these things together will give us a good understanding of what is stability with respect to all three domains. Okay, thank you. Hope you have learned much. Okay.